And I would like to take some questions during the talk, but we are a bit short on time because actually we earlier thought giving a tutorial of 3 hours. So if you have like longer questions, I'll be around after the talk. So please feel free to catch up there. And most of the questions we'll try to like handle at the end of the talk. So thank you about that. But if you have like small doubts, please raise your hands and I'll be happy to clarify. So the first part of the talk. So firstly, thank you so much. Is this working? Yeah, it's working, right? Yes. Yeah. First of all, thank you so much for all of you for joining and your attention and your interest in this tutorial. So the first part of the tutorial is going to, I'll be presenting it, and it will be around like 1 hour, 20 minutes. And then my co-speaker, Kshitij, will actually cover the mostly the online the federated part of it. Okay. So let's start with the presentation. So before we start, how many of you are aware of this online optimization, like online convex optimization, online gradient descent? All right, that's good. And how many of you are aware of some basics of federated learning? Like, all right. So the good news is we actually don't need the basics of either of this. So we'll be covering all of it mostly. It's just to see an overview of like what's the audience I'm talking to. So let's start with some motivating example first before we jump into the details of the problem formulation. Why this problem? Why do we care about this problem actually? So what is this online federated learning problem and what are the applications of it? So it turns out that consider this problem of predicting the COVID risk of an individual patient. Okay, so this is like a very important problem. We just faced this issue last 2 years. What we have is the patient features. And what we want to predict from the feature is the score, like what is the possibility that the patient has COVID. So some score in the interval of 0 to 100. And from that score, we can use some sigmoid, some kind of transformation to actually predict the probability of the patient is actually infected with COVID. Okay, so that's like a very, very simple task. And let's see how to do this. So suppose we have a patient, that's an individual patient, and we have their features like heart rate and blood pressure and whatever sample medications, all these features. And what we want to do is what we want to do is they also have a hidden label associated with them. So maybe they are actually positive or they are actually COVID negative, but this is something we don't know as a learner or as a practitioner, as a hospital, as a doctor in the hospital. I don't know. So I need to figure it out and I want to use some machine learning algorithms for it. So I'm actually saying something. It's very basics of machine learning. So basically in the x-axis I have features. I want to predict the scores. That's what my prediction is going to be. I can try to fit a linear function, or I can try to fit some non-linear functions as well. So for the time being, so to keep the matters simple, let's assume I assume that the actual COVID score of the patient is some linear function of their features. Okay, so the features is actually represented by this vector C, whatever this vector is, some d-dimensional vector, suppose. And I want to learn this linear predictor X, which is actually transforming all the features to some COVID score observation. And so this is a very simple prediction model. So suppose we have these features, we have some weights, basically our linear predict. That basically makes it W transpose X. So this summation is just weighted it by the weights we have. So obviously X is something unknown. We are trying to learn it as a linear predictor. We are trying to learn it as a machine learning algorithm or whatever practitioner. We're trying to learn this. And then once we have the predictor score X transpose C, we will be able to just use a sigmoid transformation. For those who know what is a sigmoid, it's just a mapping which takes any real number to something in the interval of 0 to 1. So it just transforms a real score to something in the probability 0 to 1. So it just takes the risk factor of the patient, X transpose C, to a probability in 0 to 1. So say that is sigma of X transpose C. And that is essentially like my prediction. That is essentially how I predict that this is the probability with which my patient has actually gone. Okay. So say I call this as y hat x. I write x in the subscript because it's a function of x. X is actually like my linear predictor. So I like it, I write it as y hat x. And how do I measure the performance? So, okay, I did some prediction. Is it good? Is it bad? How do I measure the performance? See, right? So we have seen plenty of, like first two lectures of our machine learning, we have seen plenty of measures like that. This y is actually the label, which we don't know. So we can try to measure the performance, like if it is like matching with the label. If I'm predicting something in 0, 1, I might have the threshold y hat x. I can also use the squared loss, like the squared loss error between y and y hat x. I can also use basically the logistic loss. So these are just some loss measures. So in general, I consider my loss measure to be a function. It's a function of my predictor x, okay, and the function of the patient. So the patient is actually consists of two attributes, right? Its features c and the hidden attribute y. So that's basically consists of my patient. So my loss function is a function of my prediction and the patient data, and that basically gives you the loss function. So far I did nothing. I just explained what is a regression problem. So I can try to fit this predictor x in some decision space. So throughout the talk, we will assume that the decision space is some bounded space, and the L2 norm is bounded by B. So this is just some abstract decision space. If it is a linear predictor, we can assume that the decision space is all the vectors in RD which has L2 bound B. But you can assume your favorite decision space. So we're just trying to formulate the problem a little more formally now. The objective is actually to find the best predictor x in my decision space capital X, which should minimize this loss. So which should be able to like predict the actual risk factor or actual label of the patient most accurately. So that's like my optimization objective. But that's like performance objective of my linear predictor, whatever machine learning predictor I'm trying to build up here. Some practical challenges. Okay. So far, I've been just talking about the fact that there's just one patient, and as if I'm trying to predict well for that patient. How would you even learn from just a simple data, from a single data point? You just have a single data point. You have no hope to actually fit this X star, best predictor from a single data point. You're going to overfeed very miserable. We actually want to perform well over an entire population of patients. So there's like patient one, whose data is actually this tuple CY1, CY2. All these T patients are here. Suppose you have a population of size 100, so capital T equal to 100, and you want to do better. You want to do good in this entire population. So probably a better objective is find the X star which does better, like which is actually minimizing the loss over this entire population of T people here. But okay, if the T people, if their data points CY are drastically different, it's very hard for a single predictor X star to do well over all the T patients. So possibly we should be a little more relaxed in terms of what constraint we impose on the patients. Generally, if we are sampling the patients from a demography, from a certain population, their data points should look something similar. So one simple assumption is the data points of the patients, which is the ZT vector. ZT is nothing but the tuple C and Y of that patient. So C is known and Y is something which is not known. So we can assume this entire data of the patient is actually drawn from some distribution mean. This distribution is not known to us, okay? But there is a fixed distribution from where we are drawing it. Now our objective is essentially whatever I was writing as a sum, I just turned it into an expectation. So on an expectation, if I draw a patient from this distribution, can I find a predictor which actually minimizes the COVID prediction score of that patient, of that expected loss?
Clarification, what's the difference between C and X? What is
X is actually the predictor. X is kind of the X transpose C is the linear score. X is the predictor, C is the function. Yeah, thank you. Okay, so now the problem is, this is a very nice, this is actually a very practical problem to think about, but where do we find so much data? So we are thinking of actually finding this X star, but obviously in order to come up with a good X star, which actually fits this overall population, well, we need a lot of data. and one hospital did not have so much data sample to share and even train a linear predictor, whatever a ML predictor you're trying to build up, one hospital would not have so much data. And that basically brings us to this motivation of distributed optimization. What means that there are actually several hospitals in your area, and they should somehow be able to collaborate their data, and so that they have like now jointly they have bigger data, like bigger sample of data points. They have their own patient features, their corresponding labels, and if they combine them, then they have a bigger data set. So can we actually utilize this? But then whenever we're talking about collaboration in such a information sensitive kind of data, because special features are extremely information sensitive, every individual hospital need to make sure that they maintain the privacy of the patient features. So we have to actually do this collaborative learning in a privacy preserving way, in a way so that the communication complexity is reduced as much as possible. The data should ideally not leave the local servers or the local hospitals. The data should actually, the patient data, the patient features, and the corresponding labels should actually stay within the hospital. Whatever you should communicate globally, that should be some abstract quantity, which should not reveal anything about the patient. So there are many challenges that comes up with whenever we're talking about this distributed optimization, this federated learning part. But it is at the same time also very important because we need more data to train our classifiers, our predictors. One more thing here worth considering. So one more thing worth considering here is why just try to learn one X star. So suppose this is what is happening here. So you have all your patient data, which is coming from this distribution. All we are caring about is finding a final predictor X star, which is somehow doing good on the population. But suppose in order to find that X star, you have already tested thousands, millions of patients, and they probably have predicted wrongly on them before actually finding this X star. So you're doing miserably over the time period, even if you're finding a good predictor at the end. So a better objective to look at here is actually something which is called as the regret objective, where it's basically allow us to assess how well the algorithm or the decision algorithm is actually doing over the time. It's not just I want to do good at the very end. I want to do over the time. So I don't want to be miserably predicting very badly on my patients, whoever I'm like assessing at the very beginning or towards in the middle. I want to be like good. So that's a better regret objective. So what I mean is, suppose I have M such hospitals. So M is basically the hospitals, or more generally, these are the local data servers that I have, and T being suppose the number of patients in each of these hospitals. Or you can more generally think that T is basically that how many samples I'm evaluating on this on a certain hospital. So it's basically the number of patients. So I'm predicting XTM. So this is like XTM is my prediction at tiny t, or for the user t at hospital M. So that's like my loss function, because my loss function is somewhat stochastic. I'm picking my patients stochastically. So this is stochastic loss function. But this is what I am incurring or losing on an expectation if I'm playing this predictor XTM at time t. And this is what the best predictor in the hindsight could have done. Okay, so this is essentially the difference is how much I could have done better, but I'm performing worse with corresponding to the best fixed predictor, and just take the average. So that's like my average regret objective. Okay, so is that clear? The objective? Yeah, go ahead.
What's the update rule of the XTM?
I need to compute. Yeah, you're way ahead of that. Yeah. Any other question? Yeah, basically coming up with this update rule of XTM is how the federated, like designing this federated learning algorithms in a way so that we can take advantage of this distributed data in a privacy preserving and communication complexity.
X are the theoretical optimum, or X are the best thing that we end up learning?
No, X star is a theoretical optimum.
So how do you calculate it?
I can calculate it theoretically,
Okay.
because suppose I know the distribution, I can compute that it's the distribution, what is my X star, and then I want to compute theoretically what is the performance of my algorithm. I don't have to do it in the real world, but I can always compute theoretically. Yeah.
How important is the assumption that the distribution in all the hospitals are same?
A very good question. So that's like the next slide. So I'm also coming to that. You're also ahead of time. Yeah.
Making assumptions on capital F being convex or anything like that?
Not yet, but that's also a good question. We'll make that assumption because the theoretical guarantees will depend on it. But yeah, so far nothing. It's just a loss function. Great. So that's coming to your question. It's interesting to assume that all the hospitals or patients are actually getting drawn from the same distribution. That's absolutely no way that's going to happen. So the first slide that I have shown here, where I assume that all the functions were same. So I have changed it to now F1, F2, Fn. So basically, it is called the heterogeneous setup of a federated or distributed optimization, where assume that for the mth machine or for the mth local server, the data distributions, the Z basically, the patient is actually drawn from distribution DM, which is also a distribution over the tuple, the feature and the label, but this is different from whatever the distribution is on the other hospital. Because of medication, the treatment, the procedure, many things are going to be different across the hospital. So there's no way we can assume all the data distributions are same. But if the collaboration is actually going to help us, if this aggregation of data sets are actually going to help us, we have to assume that the distributions are completely same, somewhat related. So how do we assume that the distributions are somewhat related? So this is something studied in the literature. It's called the bounded studied out heterogeneity assumption, where we assume that on an average, if you average over all the machines, and I take the gradient of this stochastic loss function of mth machine, and suppose f is actually the aggregated function. So f is basically the summation over fn's. I think I have it in my slide. This is essentially the aggregated function. So the aggregated function's gradient and the individual gradient in each of the machines, they are not too different on an average. Okay, so this essentially this xi or whatever this g xi thing, it is actually zero if all the fm's are same. But if fm's are not same, but maybe like slightly varying, this is not going to be too large. And our performance will depend on the value of xi. If they are drastically different, we can't hope to get any advantage, hope to exploit this distributed data. But if xi is small, maybe the distributions are not too different, we can still hope to like exploit the aggregation of the data sets from multiple servers. And the regret objective remains still the same. So it's exactly the same loss function. I'm predicting XTM at time t for machine M, and I'm comparing myself with the fixed best predictor in the hindsight, theoretical best predictor in the hindsight. So not only just hospitals, but this kind of applications are relevant even in mobile phone, which is like also like one of the very big application area of federated learning. We all have our local devices and we have some predictions. So whatever our smart assistants or whatever our YouTube algorithm recommending us, all these recommended algorithms are running locally on our machines. But there is a global server also which wants to collect the data from all the millions of users and try to actually aggregate the data and come up with a better model. So even like any recommender systems on mobile phones or your personal desktop, your personal IPs, those are actually the application areas of this. Not just recommender systems, even in autonomous driving, but trying to actually train a learning algorithm on a huge data set, and the data set are actually not centralized, it's distributed over some local servers. Federated learning will come. And this is essentially a figure that shows approximately the usage of federated learning in different areas of application. So there are various usefulness of federated learning, which I have already kind of covered. It's kind of a way to learn or train the machine learning model with collaboration without sharing actually the data. So it also tries to do this edge computing where data really does not leave your server. It tries to preserve the privacy of the individual data sets, individual patients or whatever data sets participating in the algorithm. To train the algorithm better, reduce the communication complexity. We don't want to like communicate to the server all the time. We want to reduce the communication because communication is bandwidth and we need to pay for it. So there are various arenas where actually federated learning tries to make a contribution. So we will be not talking about all of it, but at least some of it, the online, the robustness part of it, the online part of it, or reducing the communication complexity. So let's see. So far we have talked about the fact that we had this M hospitals and the distribution over this M hospitals could be different. But we are thinking that whenever we are drawing the same patient sample from these hospitals, the patient sample is actually coming from the same distribution in those hospitals. So given hospital, the data distribution is actually not changing over time. It's actually fixed. Is it not actually a realistic? What do you think? It's a realistic assumption to make? Over the time, new vaccinations are coming out. Over the time, your seasons are changing, summer, winter. Maybe there are also herd immunity that's getting developed. Why would the distribution of the patients would stay same over the time? In fact, a more challenging part is some of the agents, some of the hospitals may even try to manipulate the data because they are probably using some medication and they want to make sure that that medication is adapted by the government policy. Or there might be some adversarial corruptions in the data as well. So there is no way we can assume that the functions from which the patients are being, or the distribution from where the patients are being generated, that is staying the same, that's not changing over time. So that definitely something we should take into consideration. What does that mean is now for every single patient T in every individual time, in every individual machine M, we can assume that the patient is actually drawn from some distribution T and T, which is now completely personalized for that machine and for that user T. And it's almost as if I'm assuming that the distribution is changing for every machine and every user. So every machine M, there, if that is a local machine small m, is as if dealing with a sequence of arbitrary functions, small f, f1, fm2, fmt, where this fm1 is basically fmt is defined exactly like this, because the distribution can be very different. So that brings us to this objective of online federated learning or online optimization at the very just to begin with, where again the objective stays the same, and possibly we can again compare with a fixed benchmark. Though the functions are now changing widely across time, we can still try to be competitive with a better benchmark. But to be honest, a better benchmark would be a dynamic benchmark, where actually instead of a fixed benchmark in the high side, I want to be competitive with the instantaneous best. So if DMT is the distribution from which this patient is drawn, I would like to, this should have been, I think I should have used here FMT. I'm sorry about the notation. So all of this should be FMT here. But yeah, I should be like competitive with respect to the individual best at that time and for that machine. That's something which is studied in the online learning literature as the dynamic regret objective. We'll not go into it because it's complex and you have to make assumptions for how fast your distribution is changing or slowly changing or drastically changing. Based on that, you'll be able to give guarantees on this dynamic regret. So it's much more harder performance measures to study with because we are being competitive with a very dynamic benchmark, dynamic adversarial. We will stick to our earlier notation where we were actually comparing ourselves with a fixed benchmark, and we'll see how to do this optimization. So that basically brings us to the point where federated learning in its ideal form, which has this online component, which is the distribution shift, and also it should be competitive against some mixed benchmark or dynamic benchmark, and how do we actually optimize the complexity cost, how do we preserve privacy, all these things. Okay. So now from here onwards, I'm going to divide the slides in 3 parts. So I'm the one who's going to talk about the online optimization part, which is even before going to this multiple machines, we have to understand how to do this optimization, so regret optimization, even if we have a single machine and the functions are changing over time on that machine. How do I do this regret minimization well? So that's basically the online optimization part, which I'll be covering. Then my co-author, my co-speaker, Kshitij, he'll be covering essentially distributed optimization when we have n machines, but maybe the functions are still stochastic. Functions are not changing over time, but still we have n machines. How do we actually do this optimization, regret optimization? So that's Kshitij will be covering. And finally, we just presented our work on online federated learning, where the distributions are also shifting over time, and we are also optimizing across n machines. So this is a very, very initial work. There's almost no work in this literature, but this is something we have studied and just presented in this ICU in last Tuesday or let's say. So Kshitij also will briefly cover that a little bit. Okay, so we'll not be able to cover all of it, like very rigorously how to maintain privacy or how to be competitive with the dynamic benchmark. But those are basically also important areas of research. If someone is interested, I would like encourage you to go and look it up. Okay, so let's start with the first part. Before that, any questions? Or is the agenda clear? Or anything? Any questions? If there are like small clarifications, questions, please feel free to ask me. So otherwise, you might not be able to follow the slides completely to the end. So if there are notations or some small clarifications, please. Okay. So as I said, now I'm interested in a single machine, but online optimization, where the functions are changing over time or the distributions are shifting. So instead of this n machines, now I just have a single machine. And imagine the loss function, whatever, the distribution over the patients are changing at every time step t. So basically, the loss function is basically the sequence f1, f2, ft. I have removed the subscript small m for the machine because I'm just considering a single machine here. And the objective is what? Now I have just removed the summation over the machines. I just have the summation over the t. And xt is the prediction of my algorithm. Xt is my prediction at time t or for patient t. And x star is, there should not be any m here again. Something is good. So just ignore the m summation over m part because there's no summation over m. So I just still want to be competitive against a fixed dynamic benchmark here, which is x star. Okay, so the regret objectives is clear. So I'm predicting xtf at time t, and I'm competing with x star, which is a fixed benchmark in the hindsight. How do I do this? So let's, go ahead. That's what I was talking about in the dynamic part, that ideally my x star should depend on t, but if my functions are completely drastically different and you want to compete against the fixed xt star, it's very hard because the functions can be anything. You can't hope to learn anything from the earlier function about the next function. You have to assume some regularity, some smoothness assumption of how the functions are changing over time. And that's basically the dynamic regret objective. But we are not going to study that because that's like much more harder and requires more assumption. We are going to study a simple setup which is against a fixed benchmark.
So what is x star here? What's the definition?
X star is basically whatever is, so forget this m belongs there, that part is just not there, it's a typo. But just sum over this time step speed or sum over the t users, whatever is the cumulative function value, find the point of the decision space which is minimizing that cumulative loss or cumulative function value, and I want to be competitive with that. Over the time steps. I don't want to be competitive at the very end, but over the time, across the time steps, I want to be careful that I should not predict too badly. My prediction should not be too bad with respect to x star. So actually let's with a even simpler objective, simpler problem, which all of you should be very familiar with. Just for the starter, say I have a function f, and the function could be very simple. It could be just a quadratic function. Okay, x minus 2 whole square plus 5. And I just want to find the minimizer of this function. Can someone tell me which is the minimizer of this function? What is the minimizer of this function? Okay, minimizer and the minimum value. Two are different, right? Okay, the minimizer is 2. I think what you said. What is the minimum value? 5, right? And how did you find it?
Gradient equal to 0.
Gradient equal to 0. Lovely. Okay. So take the gradient, equate it to 0, and wow, you have the minimizer. But what if I don't tell you the function? You don't know the function. That's essentially the loss function, or depends on the distribution of the patient where it is being drawn. I don't tell you this. How do you do that? Well, I need to tell you something. So suppose I tell you the point, you can do this. There is the same function in the hindsight. You don't know the function. You can query any point in the domain of the function, and I can give you the gradient of the function at that point you have queried. So suppose you have queried the x at some point in the decision space in the real number, and I will tell you just what is the gradient of the function I have in my head, just the gradient of the function can be at the point x. So does anyone know how to do the rigged minimization or the optimization in that case? Yes? Whoever has seen online convex optimization should be able to tell it. Gradient descent. go in the negative direction of the gradient. Yeah. So essentially, the way to do this optimization is start from some point X and take a step in the opposite direction of the gradient, because the gradient direction is where the function value is actually increasing. So take a step in the opposite direction of the gradient. Take a small step. You don't want to take a very huge step, and that essentially do it iteratively many number of times. That will actually minimize your function. So start with some initial point x1, and for across all these users or time steps t, what you do is you query the point xt, whatever is your current prediction of the minimizer, and take a step in the opposite direction of the gradient. So that's what I'm doing, because this is something I know. This is something revealed to me by the environment. And I might have to project if my set is not in that RD. This can go out of my set. So this is just a Euclidean projection back to my set. So it's basically y is something which is outside my set x, then I project it back to the set, whichever x, minimizing this L2 distance from y. That is basically this is a simple projection step. So how does this method perform? This is actually a very strong method, and this is called a gradient descent algorithm. So note that I'm not even changing my function so far. I actually say that my function is fixed in the hindsight, and I want to do the regret minimization objective. So is gradient descent a good algorithm? How does it perform? So here is a performance guarantee of gradient descent. This is a bit of a math, but it's very easy to parse. What does it mean? So if xt's are being generated, there was a question that how do I update this xtms? So suppose if I update my xt's with this gradient descent update, so you can I can actually show you that over the t time steps or over the user, however I am performing over this unknown function, I am not going to be too bad compared to the best predictor in the hindsight, compared to x star. Why? Because the error actually goes down with a rate of 1 by square root t. So t being the number of users or type steps, t is large, see the error actually becomes smaller and smaller and smaller. So indeed, it's actually learning something which is close to the x star. Indeed, I'm actually learning a good predictor across over all these users. So it's a very strong guarantee. If someone is wondering what would be a best fixed point, because here in the first equation, I'm actually predicting x1 at time t, x2 at time 2, xt. So is there a fixed best predictor? And we can exploit convexity of the functions to make sure that convexity says that average of the function values are always greater than function value at the average. So if I am able to bound the average of the function values in the first line itself, then the function value at the average is also going to be smaller than this 1 by square root t factor. So that's also actually gives you a fixed point, which is almost close enough to x star. So that's essentially solving two problems, regret minimization as well as optimization error at the end. For those who are not aware of convex functions, it just says that any function which is convex, the average value, I mean, if you take a convex combination of 2 points, that function, that average value is going to be larger than the function value at the average. Or essentially, if you take linear approximation of the function at any point, the function value is going to lie above the linear approximation. So if you are not aware of convex functions, you can just, I have all the references. You can just go and take a look at the references. This turns out to be a very important property for us to analyze the convergence rate of the gradient descent algorithm. We'll see in a moment why. So I'll just very briefly quickly explain how the convergence rate works. How this convergence analysis goes just for a single convex function. Okay. Functions are still not changing over time. It's a single function. Let's see how it works. So imagine time steps t, okay, and my prediction is xs. That is my prediction that's coming from the gradient descent algorithm. And imagine any other fixed point x star. This could be our minimizer. This could be any point. Doesn't matter. So the first line actually comes from convexity. This line is actually just a property of the convex function by which I can write that the suboptimality gap at time step s, or for the user s, is bounded by the dot product between the gradient and the distance between xs and x star. And the second one comes from just the gradient descent update, because xs minus whatever my gradient descent update is, and we exploit the gradient information So this comes from the gradient descent update. The third line and the fourth line is just basic algebra. I just did the manipulation of the numbers a little bit. And now suppose I have bounded gradients. So I assume that the gradients of my function, whatever my decision space is, because my decision space is bounded, my function cannot, the gradient of the function cannot go really unbounded unless it's a very ill-behaved function. So I have bounded gradients. So my function is well behaved such that at any point x in my decision space, the gradient cannot be more than g. Sort of like a Lipschitz assumption on the function. And also my decision space is bounded. So whatever my decision space is, if I take any 2 points, the norm cannot be more than b. So it's a bounded decision space. And then it turns out that that expression is essentially just b squared by whatever 2 eta plus g squared by 2. And I sum it over t doubles. So there is an additional t factor. And there is some telescoping that also happens because there is the first two term actually telescopes. So you get b squared by eta, and the second term I just sum it over t norms. So this is some mathematics. It's not very hard to show. It's a very easy proof. It's taken from the book by Babek on convex optimization. So if someone is interested, go and take a look. There are much more detailed proofs there. And now if I set my eta, the step size that I was taking in the opposite direction of the gradient, it turns out that with suitable tuning of eta, b divided by g squared t, I get the rate that I have written at the top on the earlier slide. So I get this gb divided by square root t rate. Here, square root t is important because it shows that as time progresses, my optimizer becomes closer and closer to the true optimizer, or my prediction comes closer and closer to the true optimizer. Okay. Now, a funny thing here, does anything change? I promised an online convex optimization. Why am I even talking about a single convex optimization, like a single function? Yes.
Yes, slide. 1x plus 1. Is it x's plus 1? What is the difference?
Yes, this one was actually the unpredicted point. And you remember I talked about the projection step somewhere? Okay, this was the unprojected point. And y plus 1 is the projection.
This capital X is your calligraphic X.
Yes, yeah. Okay, so what I was saying is, a funny thing is, I promised an online convex optimization or online optimization where the functions are actually changing over time, and some are sticking to only a function, fixed function. So whatever analysis I'm showing you, it's for a fixed function. This function is actually not changing over time. So that's not fair. But actually, let's try to throw this gradient descent algorithm even an online sequence of functions where f1 is actually changing over time. Because me as a learning algorithm, I don't know much actually what's going in the hindsight. I maybe just blindly play this gradient descent steps. And does anything change in the analysis? So turns out actually no. The gradient descent is actually even the optimal thing to do, even for an online sequence of functions, as long as I am comparing myself against a fixed benchmark extra. So note that in this analysis, it's exactly the same analysis that I explained in the earlier slide. Modulo, now I have changed all the f to fs. So as if like now my f is a time-dependent function, it's changing over time. But if you look closely in the analysis, nothing breaks in the analysis. The same telescoping happens here because it's on the x, it's not on f of x. The telescoping happens and you get the same rate. So that's basically the beauty of this online gradient descent kind of algorithm, that even if the functions are changing over time, it can adapt itself and still be able to find the best best predictor in the hindsight extra. But is it the case always? So for now, I was talking about a convex function, but what if I put some more structures on the function? Maybe the function is slightly better behaved. So in which case can I actually, like, is there a difference between the convergence rate of this gradient descent algorithm between that class of functions and when the class of functions is actually changing over time? So is it the case that this online behavior really does not hurt any time, or it actually doesn't hurt for convex functions maybe, but for slightly more well-behaved functions, it does affect? So let's assume more properties on the convex functions. So some of you might already have seen these properties. Just for briefly to introduce ourselves. So one of the property of a convex function is a smoothness. So it says that the function is convex, but at the same time, the function is well approximated. The value of the function at any point x can be well approximated by its quadratic approximation. If I take like second order Taylor series of the approximation of the function, my function value should be upper bounded by it. So essentially says that my function should not change too drastically between 2 points. It also says that the gradient of my function is actually like h Lipschitz if the function is h full. So the gradient of the function does not change too much between 2 close points sometimes. So that's a nice property of convex functions, and we'll see how we can exploit this property of the convex function. And gradient descent actually performs well when the function is like fixed. It can perform better than 1 by square root t convergence that we have seen before. There are more properties of convex functions, which is called strong convexity, where it says that the function is convex, maybe, and it also has enough curvature in it. So the strong convexity property says sort of the dual version of smoothness. So it says that at least the Hessian should have an minimum or something else. So there's enough curvature in the function. That's what the strong convexity says. There are various properties of convex function that has been studied in the literature. So if someone is interested, you can either go through this Bubek's tutorial, Bubek's book, or Hassan's online optimization book. Those are very useful tutorial books references for it. So one example of a function which is simultaneously smooth and strongly convex is just the L2 loss. Okay. The h and L, both of them are actually equal to 1 for this function. So this is a very well-behaved function in general, but individually we can come up with functions which satisfies one of the property and not the other. So now let's assume that we have a function which is convex and also smooth. Okay, so can I actually have a better convergence guarantee of this for this kind of a function with gradient descent? Remember in the earlier slide, I showed that the convergence rate for gradient descent was actually 1 by square root t. Thus, if I assume on top of it a smoothness assumption, my convergence rate actually increases. It actually gets better. Because a 1 by t convergence is always better than a 1 by square root t convergence. If it is a 1 by t convergence, it means that you just have to take linearly some many number of steps. You're already like 1 by number of step size is good, closer to the optimal point. So it's a better convergence rate, and also the smoothness can be exploited by gradient descent algorithm to have a better convergence guarantee. The analysis is slightly complex, so I'm definitely not going into the details of it, but it's still simple. I still have the analysis here just to show you that how the analysis breaks when the function is actually changing over time. It's actually not a fixed function, but it's changing over time. So, this is just I'm starting in the earlier ways. Now using smoothness and convexity, I can write the first line. The second line is basically I denote this delta S is basically the suboptimality at times step t. I do some algebra, and whatever this algebra is, it actually telescopes somewhere. But this telescopes is actually happening in terms of the function value. See, this telescoping is not in terms of x, but actually the function value, because delta is defined in terms of the functions. So if the function is fixed, definitely you can do this and you can get this 1 by t kind of a convergence rate. Of course, you have to tune your step size slightly differently. But if the function is online, it's actually changing over time. You can't do this telescoping thing here. Actually, it breaks. And if it is, the functions are actually changing over time, you can't do better than 1 by square root. In fact, there is a lower bound for online sequence of functions, which we can show that no algorithm, forget about gradient descent, no algorithm you can come up with for an online sequence, which can do better than 1 by square root t convergence for any arbitrary sequence of convex functions, even smooth functions. Okay. Am I going too fast? Is there questions, or so far is the broad picture clear? Whatever I'm talking about.
Just for 1 over t upper bound. Here you say you can only achieve 1 over square root.
This is for the online sequence. That upper bound was for a fixed function. So I'm saying like I can always construct a sequence of functions f1, f2, ft such that I will make you incur, no matter what algorithm you come up with, I will make you incur 1 by square root t of convergence. Yeah. So I'm trying to like show the difference between fixed function optimization versus online optimization. Yes.
This is without strong convexity assumption.
I will show this lower bound on a linear sequence of functions, and linear functions are like kind of smooth and also strongly convex, but the parameter of those are zero in some sense. The strong convexity parameters are zero. So yeah, this lower bound will not depend on the smoothness parameter or strong convexity parameter, but
It's not a strongly convex function.
it is a strongly convex. But if my linear functions are considered to be like smooth and also strongly convex.
That seems strange that you assume linear function to be strongly convex.
I mean, so the thing is, this is a matter of debate, to be honest, and this has been a debate over even in the optimization literature, whether we should consider the class of strongly convex functions in this class. You may feel free not to consider it, but if we can come up with a better lower bound, that would be like a conference paper. So don't know if we don't know if we can come up with a lower bound specifically for the class of strong convex functions, online strong convex functions. But yeah, for linear functions, the proof is very easy. So I can show you that proof. And generally, there is no upper bound algorithm available which can do better than 1 by square root, even for strongly convex functions. We'll see the rate in a moment. So let's try to look at the construction of this online algorithm. Of this lower bound for online sequence of functions. So consider the decision space. So suppose our decision space is essentially any point inside a unit hypercube. So think the unit hypercube in the dimension. And at any time t, suppose I construct my function to be some vt. This is some linear function. This is some linear hyperplane. I don't know what this hyperplane is. This is some unknown quantity vt. And then I have my function is defined on x. So I am predicting x. So this is how I define my function. It's a linear function. And suppose my vt is actually drawn from the extreme points of the unit hypercube. So I even know that my vt has only 2 to the d choices, and it's uniformly drawn from the extreme points of the hypercube. And that's how I define my sequence of functions. So it's not even like fully adversarial sequence. This sequence of functions are actually like kind of stochastic sequence, because I know this whatever my linear function is actually stochastically changing, not even changing very adversarial. So even in that case, you can't do better than 1 by square root t convergence, no matter what algorithm you use. How? Because this is our regret objective, right? So when we have stochastic sequence of function, the regret objective essentially looks like we have to take an expectation over the vt sequence, because vt is essentially like our functions, because vt defines this linear function, and so we have to take expectation over vt, and the objective inside stays the same for a particular realization of this vt sequence. Note that this expectation, the first expectation, this is actually always zero, no matter what xt you choose, because vt's are basically zero vectors on an expectation. And by linearity of expectation, you can always show that this term is always zero, no matter whatever your choice of xt's are. Okay, so really the point lies in showing that whatever the minimizer, whatever the God predictor is, can it exploit or can it do something better than zero? Turns out that it can. So if we try to understand and analyze this second quantity here, because there's a negative sign in front of it, we should be able to, like, with some just basic algebra and some concentration bounds, we should be able to show that this second term is essentially of the order of minus d square root t, when the vt's are drawn from the extreme points of the hypercube. And so 0 was our performance, and the performance of the optimizer was minus d of square root t. So your incurred regret for any sequence of xt's is essentially d square root. So that gives us the d square root t regret guarantee. And note that b and g, basically the boundedness of the gradient and the bounded diameter in our case, both were actually square root t. So it actually shows that the minimum rate you can achieve is bg square root t. You can't do better than that for an online sequence of functions. Okay, so yeah.
Can you explain why is this inner product vtxt 0?
vtxt 0 is because vt is actually, look at the coordinates of vt. It's drawn from the extreme points of the unit hypercube. So coordinate by coordinate, expected value of vi is always 0. So summation, the expectation over, like, expected value of this v vector for every coordinate is 0. So no matter, because it's a linearity of expectation, you can push this expectation inside the summation.
XT don't we have XT is how is XT generated using some algorithm, right?
XT is generated using some algorithm. Yes, it's whatever algorithm you have in mind.
So but XT is independent of
Because VTs are independent over time. VTs doesn't have any dependence. So that's why. Even if you make your XT dependent on VT, VT plus 1 doesn't depend on VT. That's why. That's a good question though. Okay, so the moral of the story here is basically you have an online sequence of functions, even as simple as a linear function and a stochastic sequence of functions, no algorithm can do better than B square root T, or basically BG square root T. So that's the situation we call an optimization.
But it was this the last step went from an expectation to what is the
D square root T.
no in the previous step, yeah.
This was I have taken this because I was summing over D coordinates. Yeah, that comes out. This part actually requires some concentration argument, but it's simple. It's not very hard. You just have to like take two, I think, binomial distribution and difference of two binomial distributions and how it behaves. But it's easy to compute this. For the interest of time, I will maybe if you have more questions, I'll be around. I'll be happy to answer. In fact, I have more slides, so I can even show you detailed proofs if you want later. So briefly summarizing, so this slide essentially shows that if your function sequence is fixed across time, it's not changing over time. So this is how the rates look like. So we have already seen the proof of the first rate, which is GB square root T. And the second rate also we have seen, which is actually like 1 by square root, 1 by T, which is a better convergence rate. Turns out that if you use strong convexity or strong convexity and smoothness both, you can get even better rate when the function is fixed and not changing over time. In contrast to it, when the function is actually changing over time, set1 and 12t, the rates looks pretty bad. So the rates is essentially GB square root T for both smooth and strongly convex functions. Both convex and smooth functions. If we have strong convexity, and if we have smoothness and strong convexity, we can actually get better rates. I think I said something like you don't know how to get better rates, but turns out that you can actually get better rates. So the function has strong convexity. You can't get better rate when we have bandit information, so I confused with that. You actually can get better rate when you have strong convexity or smoothness assumptions. But I did not, it's essentially gradient descent is what is going to get this rates, but we are not going to explain or discuss it. I have the two very nice lovely references here. So Bubek's book and Hazard's book. They individually covers a single function optimization and online function optimization. So just please go and refer to them if you are interested.
There should be a T there.
Well,
The denominator.
there should be. That's correct. There should be a T in the denominator in both because right. That's correct. Yes.
Thinking about the online smooth gap. The online smooth gap, where is the H come?
Go ahead. Once more. Sorry.
The smooth part of the online setup.
Yes.
Yes. You're using H smooth, and where is the?
It doesn't shock. You can't exploit it. Even if the functions are smooth, you can't exploit. This is the best rate the gradient descent can give. I'm not very sure if there is any other algorithm which can actually improve this rate. Maybe something like an ellipsoid or cutting film methods can give a better rate. I'm not very sure. But gradient descent actually gives the same rate. It can't exploit smoothness. It's very different from what behavior in the fixed function setup, but in the online setup it can. Okay. I have some more things to cover. At least I want to cover the more interesting feedback setup here. So far we have been assuming that the query will query a point X, and even though we don't know the function value, we can actually see the gradient of the function in the query point. That's a strong assumption. That's a lot of information about the point you're querying and the function. How about we don't have it? How about we just have a bandit information available, which means that instead of showing you the gradient of the function at that point, I'll only show you the value of the function. Like you play some X, I'll only show you whatever the loss of your function is in that point, in that predictor X, but I'll not show you the gradient. That's a lot more restricted feedback. And you definitely cannot perform gradient descent here because gradient descent requires the knowledge of the gradient to do any updates. So how do you do the optimization in that case? And how does the convergence rate look like if you don't have the gradient but only have the function value? And this is called the bandit information in the bandit literature because essentially you just see the loss of the point you're playing and nothing else. So it's just one fancy way to say it's bandit information or just the function value information. So the idea here, which is a very cute and nice idea, it says that we can estimate the gradient even if we don't have the full gradient. We can estimate the gradient of the function at the point that I have queried just from its function value. So on an expectation, I can find a vector which is on an expectation kind of behaves like the gradient, even though I don't see the gradient but only the function value. So it's a little easier to build this intuition from one dimension. So assume that I have a function in one dimension, which is from R to R, and the function, we all know this, right? So if we can query 2 points, w plus delta, w minus delta, and delta tends to 0, this is essentially the limit exists if the function is differentiable, and if prime x exists, this f prime x is a valid function, it exists. So this limit delta tends to 0 is essentially the derivative of the function if it. So I'm assuming the function is differentiable, the derivative exists, and it's f prime. So a slightly different way to look at this expression is, suppose I have now querying u, which is a random point. U could be +1 and you could be -1. So consider the interval 0 and 1, -1 and +1. And you can query +1 will have probability, -1 will have probability. So I can always write the above expression like this. So as is like I'm querying random direction plus or -1 and querying a point and just dividing it by delta. So that gives the f prime x, the derivative of the function. If I try to generalize the same idea in the d-dimensional case, it turns out that if I draw a u, because now in the d-dimensional case, I have to draw the vector. So it's essentially a unit direction. So in one dimension, a unit direction is either +1 or -1, because you can only move in these two directions in real time. In the d-dimension, the notion of unit direction is like you can play anything in the surface of a unit sphere, because all of those are actually like unit vectors. So you draw a unit vector from the sphere of radius 1. You have a question?
Yes. So the delta in the second line has to go to 0 or?
The delta, we can't set the delta to be 0 because in that case, our estimated gradient will become.
But the delta has to tend to 0. And in the.
Right there. Yeah, the limit, I wrote the expression. The limit delta tends to 0 is still there. I did not just write it. Imagine.
Okay.
Yeah.
And then in the last and in the approximate.
This is not delta equal to 0. So that's why I have put it like this.
So this is for the small delta. So
yeah, I have to allow some slack delta because I can't set my delta to be 0. That's like because then my estimator is essentially an infinite vector. So I have to deal with small deltas, but that's okay to deal with that much of delta. More questions? Yeah, so what I was trying to motivate is this illusion in one dimension can be actually translated in 3 dimensions, where you can draw a unit vector from the unit sphere, like any unit direction, and query a point in that any point x and a small perturbation step in that unit direction, and then come up with this estimate, like multiplied by mu, multiplied by d, and divided by delta. Turns out that this quantity is motivated from that. There is, of course, a proof available for this, which I'm not going to do that because rigorous vectors and that stuff. It's approximately the gradient at the point, gradient of the function at the point x. And note that what do we need to evaluate this? We just need one single evaluation of the function in this point x plus delta. So it's just one single evaluation, which on an expectation behaves like the gradient of the function, which I actually want for gradient essentially what. So it's a very powerful result. And if I be a little more precise about those approximated terms, this is the precise statement in the yellow. So assume another function f hat, which is sort of a smooth version of this function, original function f. So take this b. So it's sort of like a delta smoothing around my original function f. That's how my function f hat is defined. It's not really important to go into the details of it. Turns out whatever my estimated quantity was f of x plus delta u times u, that expectation is actually equal to the gradient of this smooth function f hat. And this smooth function f hat is not too far from my true function f. And that's the reason I can actually deal with some delta, because I will actually optimize this f hat. But if I optimize f hat, I will be optimizing my two functions, because these two functions are not too different. We essentially vector drawn from a ball of unit radius, but yeah, I did not like mention all the details. Yeah, V is a unit vector from ball of radius 1. So yeah, it is, I think, defined here. So coming back to the problem, so we want to now do online optimization, rate minimization over this online sequence of functions. It's very hard, like, because the functions are changing over time, and what you get to see is only the value of the function, only a fixed. So the algorithm is called bandit gradient descent. The only trick that we use here is, instead of, I have initially my step was xt minus eta t of gradient, right? I don't have the gradient. So I have gt. gt is my estimated gradient. And how do I compute this gt? Essentially sample any unit vector in dimension d, query the point xt plus delta ut. Xt is like my current estimate of the minimum. So I can initially start with some x1 and I keep updating my xt. So find this estimated vector gt, which estimated vector we show almost approximately the gradient of the function at the point x, and then make a step in the opposite direction of the estimated gradient project. Same algorithm, instead of grad fxt, we are using dt, and very small details here. I have to predict it slightly within my set x here. So suppose that x was my original set, I have to now predict it within 1 minus delta radius of the point, because I'm doing xt plus delta ut. So if I stay slightly inside, if I take a delta step, I still stay inside. So that's a small step here. That's not very difficult. Yeah.
So essentially what you've done here is you've replaced exact gradient evaluation with a Monte Carlo estimate.
Yeah, because that's the best I can compute. I don't have the gradient, I can just have the estimated gradient.
And you use one sample in this algorithm. In practice, is that what's done, or do people use multiple?
If you can use multiple samples, you can actually do better. We'll see. Yeah, if you can use multiple samples, you can do better. Because your gradient estimation will look better.
And so computationally, is it more advantageous to multiple samples at each step, or take more steps?
There is a trade-off between, it depends on application to application. So suppose if you're querying say it's a patient's loss, and that's very hard. So you can't actually like do random samples over 10 different patients, because it's actually affecting their health condition. But if it is something like a mobile phone prediction, like a video recommendation, then probably you can afford to do it, like multiple samples on functions. It depends on the application. But yeah, it's a trade-off between how much you can suffer on the current time step versus how much best you can do at the end. Because if you can do multiple queries, you will do better at the very end. You will do better.
Thank you.
Yeah, that's a good question. Thanks. Okay, I'll actually rush a bit because I have to like talk about also this multi-point convergence. But this is the main idea. I think everybody got the main idea. I also have the slides for the proof. So we'll just quickly see how this method performs. Remember the earlier rate we had with gradient descent was 1 by square root t. So do we actually get 1 by square root t rate even with bandit feedback, or do we get something worse? Better is not, it's too much to hope for, but at least do we get 1 by square root t? So if we actually analyze our gradient descent algorithm, bandit gradient descent algorithm, or on a convex sequence of online functions, I can basically initially start with the step that I'm as if doing online convex optimization on the full gradient of this function f hat, because I told you that my gradient estimator is actually on an expectation, the true gradient of the function f hat, which is almost the f function, or ft hat and ft function. So the initial step comes from the online convex optimization, online gradient descent step. And then basically, because f hat is slightly different from ft, I have to take care of the Lipschitzness and all this assumption that how close my f and ft are. So that things I have to take into consideration to finally do some manipulation, tuning of parameters. Actually, nothing going on. This entire rate follows from the full gradient rate that we see in the last few slides earlier. So all I'm trying to say is that rate with some parameter tuning gives me the rate of t to the 3/4. So if I divide it by t, it essentially tells me the rate is quite optimal. The rate is actually 1 by t to the 1/4. So note that this rate earlier was 1 by square root of t, or 1 by t to the 1/2, and now it has gone as bad as 1/4, which is like a lot slower convergence. And this is actually sort of you have to pay because you don't see the full gradient, but you only see a function value and estimating the gradient. So it's suboptimal. No, this is an upper bound. This is the upper bound, which is no, this is not lower bound. Again, it's the same trick I'm doing. If I'm doing well on the average of the functions, I can always find that the function at the average value would also have the same convergence, but that is not great as we see. This 1 by square t to the 1/4 is kind of what we can do, assuming convexity, bounded gradients, and bounded. And I have this table. Of course, I'm not going to talk about all possible like how the algorithms and convergence analysis work for different properties of the function. But turns out that if the function is linear, you can actually get a 1 by square root t rate, which is sort of the rate we got with the full gradient. But now it's only for linear functions you can do this rate, and this is also not online gradient descent. This is slightly more complicated algorithm. Some online gradient descent kind of algorithm is done here. So I have the references for all of this individual convergence rates, which all of them are individual here conference papers. So you can go and take a look at it. If it is smooth, we get a slightly better rate t to the 1/3. If it is strong and also smooth, then we get like 1 by square root t rate within that case. So kind of the broad picture of what we can do with bandit feedback. And there has been a lot of struggle in the online optimization literature to actually improve this 1 by t to the 1/4 rate of gradient descent, or something like 1 by t to the 1/2. And there has been enormous amount of work. Some I'm citing here, like the paper by Hazan, a paper by Zubik, Latimore. They all tried coming up with 1 by square root t kind of a rate for online sequence of convex functions. But turns out that the dimensionality dependency, the dependency on the dimension, each of these rates are quite bad. The last algorithm is so far the best rate available, but the algorithm is, I think, is not even this is like an existential proof that such an algorithm might exist. I'm not very sure if the algorithm is there for this. So as you can see, there is no simple algorithm known so far in the literature for this problem of online convex optimization. I mean, basically online optimization with bandit feedback, which gives d divided by square root t kind of guy. And it's an open area of research. So if you have some ideas, you're welcome and feel free to attempt it. Okay, so I think I'll just explain something very quickly here, following up from his question, that if I have instead of 2 points, I was so far restricting my feedback to just 1 point, right? So you query x, I give you f of x, or you query x, I give you f t of x, if the function will change over time. If I just slightly tweak it and I say I will show you the function, I'll let you query 2 points instead of 1 point. You can query 2 points, whatever points you want, and I will give you the function values at those 2 points. This is called basically 2-point feedback. It turns out that whereas with 1-point feedback, we could not get any optimal square root t kind of guarantee, with 2-point feedback, as algorithm as simple as gradient descent can achieve this square root t rate very easily. Which is kind of a surprising fact that just from transitioning from 1 point to 2 point, you can do so much better. So how do we do that? So it's exactly the same algorithm, because we are mostly talking about gradient descent here. Instead of 1 point, I'll be using 2-point evaluation now to compute my gradient. So just sample a vector u, which is a unit direction in dimension d, and query 2 points, because I can query 2 points now. X plus delta unit span is available. So symmetrically 2 opposite points around xt, which is my current estimate of the minimizer. And then this is my new estimate of the gradient. You see, instead of just earlier I just have your FT, one of this point, now I just have a difference. And that itself makes a rate so much better because we can do a lot of variance reduction in the gradient with this kind of an idea, and that basically pays off in the convergence analysis. So it's quite a lot of magic that how 2-point feedback can drastically improve the convergence rate so fast. The rest of the algorithm is exactly the same. You take a step in the opposite direction of the estimated gradient, you project it back to 1 minus delta set, and exactly the same thing. So let's try to see how this algorithm performs. Go ahead.
Yeah, so maybe notation clarification.
Yeah.
Previous slide.
Yeah.
So what's highlighted in yellow? Yeah. So right now I have f of xt plus delta ut minus f of xt plus delta ut that is equal to 0, right?
Yes. So sorry, what is 0?
So within the bracket,
Yeah.
you're subtracting that's minus. Okay, great. So okay, and I guess what I missed is so this is intuitively what I would expect to do. So in the 1-point gradient, we're only subtracting x.
This value, and we were multiplying it by the unit vector.
I see.
We're not able to subtract anything, but here we are actually able to subtract the symmetrically opposite points, which is paying off in the
Okay.
analysis.
Great. Thank you.
Yeah.
Thank you.
Thanks. Thanks for the question. Okay, so let's see how this algorithm now performs actually. The next property is the same. So on an expectation, whatever my GT is, that symmetrically opposite points, and whatever the estimator of GT is, it's actually still on expectations gives the gradient of the smooth function f hat. So that part remains the same. But if I actually analyze the norm of this expected gradient, estimated gradient, this norm earlier was lot bad. I had it in my analysis, but I could have explained so that the estimator of this L2 norm, we had to upper bound it to the proof because we need the boundedness assumptions on the gradient somewhere in the proof. So this was earlier too bad. It was quite large, but now we can show. In fact, it was dependent on delta. But now we can show that because we are doing the symmetrically opposing points, we can use some consideration of convex functions and some more tricks to show that this norm on this expected gradient is much smaller. It's just dg squared. It's very too small, and that's g is basically the Lipschitz or the gradient, the boundedness on the gradient of the actual function f, or you can think it like a Lipschitz constant. So this is just a proof. I'll not go to the proof of this, but these are the two properties in yellow which are going to exploit it in the convergence analysis. So we'll see how. This is a proof of how we bound the norm. Okay, so as before, we know that on an expectation, my GT gives the gradient of this function f hat. So as if I can do a full information analysis on the sequence of function f1 hat, f2 hat, f3. So I just have written it for the full gradient information analysis on this online sequence ft, f hat t, and that gives that rate, which is essentially the bg square root rate that we have seen earlier. Now it's just a problem of converting this f hats into ft's, and whenever I'm using g here, so the norm, the boundedness of the gradient, I'm using the earlier bounded. So dg square, that's the bound I have been using. So I'm getting a better rate in the right hand side. It might not be clear to you, but if you just take a look at the analysis in this paper by Shami 2015, it will be very clear how this rates improve the analysis. So finally, if I just take care of the fact that f hat t and ft are kind of similar, use the Lipschitz assumption there, and then change the sides of different mathematical notations, do some math. And finally, you already see if I tune my parameters nicely, I get a square root t kind of rate. And this is like, I'm not dividing it by t. So if I divide this everything by t, I get a 1 by square root t convergence. And trust me, all of this is possible because I have a better bound on this expected gradient vector GT, which is possible because of the 2-point feedback. So that's the takeaway of this slide. How it can gives us a 1 by square root t rate so easily. In fact, if you, again, following this question, if you interrupt 2-point query, if you can query m points, M should be something between 2 and D plus 1. If you query like, or D, if you can query order D many points, you can get a rate with online gradient descent sort of algorithm, which is like GB divided by square root M. To see if M is kind of order D, you almost sort of can estimate the true gradient of the function. And you get the rate, which is with full gradient information. So if you can actually make multiple queries, even bandit queries, order D multiple bandit queries, you can recover the rate with bandit information, but you can recover the convergence rate with full gradient. So which is also a very strong result. Okay. So you might just have to summarize very quickly. What we have seen is the motivation of this online optimization problem, and we have seen like why the distributed optimization is important, because we have to accumulate data. We need more data to train our models. So that is and the data distributions can change over time. The function sequence can change over time. So that's the motivation between for online federated learning. So in my portion, I actually covered the part of online optimization, but the function sequences are changing over time. But it's not, there's just a single machine. So we saw how the convergence rate look like for gradient descent, for simple gradient descent kind of approach when the gradient information is available for a fixed function, for an online sequence of functions, and for bandit feedback when you don't have the gradient information available, but still the sequence is online, how the convergence rate of gradient descent look like. We also see how we can actually improve the gradient descent convergences for 2-point feedback with 2-point feedback. So I'll just end in 1 minute with some advanced topics which would be of interest to some of you who are interested in more optimization related area, especially online optimization. So there are more advanced topics like why just restrict ourselves to a bandit feedback. There can be even more limited feedback that we can thought of. So sometimes actually if you are giving me 2 options, maybe the loss is not clear to you. No one is actually also giving you the loss, the function at the point of query, but only going to give you that whether among 2 predictions which one is better, which is sort of like a preference feedback, which is even weaker than a bandit feedback that you can hope for. So there the model of the optimization problem would almost look as if like instead of querying a point xt in the decision space and seeing the feedback ft what you can see is what you can query is actually 2-point fx xt and xt prime, as if like these are two predictors. Yeah.
Sorry, but like question. Is there any kind of actional policy in bandit? Generally, in bandit, there's a policy to minimize the regret.
This is essentially the policy, because there's no so whatever my xt is the policy, that's what it is breaking. Is your question related to reinforcement learning stuff?
Yes, actually.
So maybe we can take it later, but I think I can that because I have to like finish it. My next speaker need to start. So yeah, so all I was saying was just to motivate some more open directions and new areas of research, which is being conducted right now with this online optimization literature. Instead of like 1 point, I can query 2 point, and all I can see is which of these 2 point has a higher function value. So almost like a preference feedback that, oh, I like this predictor better than that predictor, but I don't know how the losses look like. I just know that I like that predictor's performance better. That's the only kind of feedback you get. Or maybe like you can query a subset of points, but only what you see is which of this predictor among the subset of predictors actually like performing best. So those kind of preference feedbacks, how do you do well? In fact, there could be some sort of threshold feedback also, that maybe like you're predicting, and if the prediction, the utility of the prediction is above a certain threshold, then only you see a feedback, otherwise you don't see a feedback. For example, you set the price of an item. If the price of the item is actually smaller than the utility you have in your mind for that item, then only I'm going to buy the item. That's like the feedback, otherwise I'm not going to buy the feedback. So it's like a threshold feedback. So similarly, very many limited feedback are actually very practical and available and kind of needs to be studied in the literature, which are really not studied much. So I have some recent work with 2-point feedback and the preference feedback. I just don't have the time to cover it. I just have the slides for so whatever reasons, if someone is interested, I can discuss this later. So I'll just skip these things quickly. Yeah, so as I said, finally, the further restricted feedback models are available with thresholded feedback, with subset-wise preference feedback. or even with more limited partial ranking feedback. So I just can view like my top 10 rankings or something. I like that this many predictors, I don't know what is happening with the other predictors you have. So various kind of limited feedback we can consider, and optimization is an open area of research for those limited, even more limited feedback. So with that, I would like to conclude there. Yes, I have one question maybe. So this part is included in my Kshitij will start from the second part. I can take any question.
I think I might have missed it. So going back to original motivation, you have samples from which you are getting for your loss distribution. I guess there's going to be some sort of estimation error from going from samples to F. That'll also impact your regret and algorithm.
Yeah, so that is basically estimation error kind of a problem, like the true error on the expected distribution and the estimated error from the sample I have drawn. Yeah, so those things.
Okay, so the assumption here was that you knew the F.
The assumption here is as if like even my function. So in my part, I assume that my functions are drastically changing. Like I am actually evaluating my predictor on exactly the functions I have seen so far, but I'm not evaluating on the expected function. I'm actually evaluating on this function. Yeah. So thanks a lot, everyone. And you have more questions. If you have more questions, I'll be very, very happy to answer. So, Kshitij, how do we join?
The next is listening happens.
Okay. So I think my co-speaker. So how do we jump after this? He's going to like. I have to like stop sharing, right?
Yes, I'll take care of it.
Okay. So I can like speak for 5 more minutes because my.
Sorry. What I mean to say is we'll take a 5-minute break now so we can test the tech for the next speaker.
Okay.
Okay, thank you.
So the fact that 6:30, so it's like.
Yeah.
Just like Kshitij.
In the paper. So Kshitij is going to talk about first distributed optimization with just in a homogeneous setup, and then he's also going to talk about online federated optimization, which is going to be super interesting. So over to you, Kshitij.
Hi, everyone. Good evening. So thanks for coming again in person. So we are running a little bit short on time, so I'm gonna change the plan slightly, and I'm gonna skip some of the analysis part which I was gonna go through because we have roughly about 1 hour before I'm assuming all of you are really tired after the entirety of the conference. So, but the hope would be to give you a good picture of the entire set of results here and also give you some references so that after the talk, if you want, you can go through those references and get a more clearer idea of the analysis and what are the open gaps and challenges here in this literature. Unfortunately, I couldn't make it in person to Pittsburgh, but if you have any questions related to my part, feel free to email me, and if Aadirupa could answer some of those, she'll be there too. But yeah, feel free to reach out and I'll try to answer whatever I can and direct you to other resources people if I can't. Okay, so without much further ado, let's start. Okay, so Aadirupa already gave you a very good motivation about why we want to do online federated optimization, but I want to take a step back and start talking about federated optimization a little because this is not something everyone might be familiar with. And it says algorithms and analysis, but I think I'm gonna be focusing mostly on algorithms and convergence rates we can get. Okay, so let's start talking about federated optimization. So before that, let's go maybe a decade or so back and talk about a very simple canonical distributed optimization problem. So you have m different objectives. We saw there were like m different machines or clients in the first part of the tutorial. And you want to minimize the average objective. In particular, you want to minimize this objective where you take the average over FMs, and then you're trying to find a single consensus model which works well for this average objective. Why would you usually want to solve this problem? Usually you want to solve this problem because it's a proxy for a harder multi-objective optimization problem. In particular, you have these objectives and you want to come up with models which work well for each of these objectives and somehow also use the information coming from one objective to get to an optimizer for the other objective, etc. But this multi-objective optimization, like all multi-objective optimization problems, is hard. And it's a very reasonable proxy to just average things and try to instead optimize the average objective. This is a meaningful proxy or a reasonable proxy only when FMs are similar. So Aadirupa already talked about the homogeneity and the heterogeneity issues in the previous talk. And what I'm trying to say is that when these functions are similar or they are moderately homogeneous, or like there's not much heterogeneity between the functions, and I'll formalize all of these things later, then you can hope to work with this proxy and still do well on the multi-objective optimization problem. In particular, with a bit of abuse of notation, the min value of the first objective, which is the average objective, is going to be similar to the min value of each of these objectives. So it's an abuse because multi-objective optimization, it's a tuple, it's not a single value, but the average value is going to be equal to the minimum value of each one of these objectives if you were to use an individual model for each one of them. So this is a meaningful proxy in this setting. And for this talk, for the most part of this talk, we are going to work with this working assumption that these things are actually similar so that it makes sense to collaborate, it makes sense to solve a federated problem. I'll actually revisit this assumption towards like the later half of the talk and talk a bit about personalization and what are maybe the more reasonable things to do here when the functions are not similar. Okay, so this is a problem. And one example of this problem, I think Aadirupa already mentioned the COVID-19 prediction problem, is when you have a stochastic objective. So you have some distribution on each machine. Let's say DM is the distribution on the mth device or machine, and F is a loss function. So in the previous part of the talk, we looked at squared loss or logistic loss, or it's some loss function. It might be convex, it might be non-convex, it's just some loss function. And you get samples from this distribution and you're trying to solve this optimization problem where you're minimizing this expected objective. And without further constraints, we really understand this problem, right? Because this is just a stochastic optimization problem. And the default class of algorithms, which all look like SGD, like SVRG, Saga, Adam, which you might or might not have heard of, are well understood, both theoretically and empirically. At least for convex problems, we very reasonably understand what is the convergence guarantee, what are the lower bounds, and how to run these algorithms, how to tune these algorithms, what are some heuristic ways to run them in practice, etc., etc. And essentially, we know all of this for the above problem, the distributed problem as well, because it can be viewed as a simple stochastic optimization problem by looking at the uniform distribution of the machines and recasting it as a stochastic optimization problem. Of course, here I'm assuming that when I say it's a stochastic optimization problem, you have access to appropriate stochastic gradients, but not getting into those details. We're going to get into them later anyways. So, okay, we understand this problem when you look at it as a single objective. When you have as many accesses to these objectives as you want, you can access their gradients, stochastic gradients, whatever. It just becomes a stochastic optimization problem. But usually you do not have unconstrained access to these objectives. There are constraints. And one of the major constraints is communication, which I'm going to come to in the next slide. But before that, these algorithms, SVRG, Saga, or Adam, you might know of them because these are the workhorse algorithms of modern machine learning. So most like modern machine learning, like big models, big neural network models, which you want to train, are trained on multiple GPUs. You have some data split across the GPUs and you're trying to optimize the average objective. So this is what usually the objective will look like. NM is the number of samples on, let's say, some mth GPU, and then you're trying to optimize the average objective. So you can reinterpret it in the previous notation by thinking of DM as the uniform distribution on NM points, and it's all the points on the mth GPU. F is some neural network parameterized by weights X. So then it usually becomes a non-convex problem. So SGD with momentum and Adam are the most popular optimizers if you train the neural networks, and if you work with applications which use neural networks, you might already know that. What federated learning does is it adds more constraints to this distributed optimization problem, as I said. So you do not have unconstrained accesses to these objectives or these data points anymore. There are more constraints to the problem. And to talk about the constraints, I should mention two flavors of federated learning, which are really popular. One of them is going to look very similar to the canonical distributed optimization problem you might have in your head, which is perhaps something like AWS servers operating throughout the globe. And another one is going to look a bit more different and maybe something people think of when they use the word federated learning. So the first model, which looks a bit similar to canonical distributed optimization, is cross-silo federated learning. As the name suggests, there are m different data silos. They might or might not be geographically separated, and usually you think of 2 to 100, that's the order of clients you're working with. You often have privacy concerns as, okay, maybe the data in one silo is not allowed to leave the country where the silo is situated, etc., etc. And another example is you have different organizations, let's say different hospitals, as in the example in the first part of the tutorial, and they have some incentive to collaborate, like to perhaps come up with a model which is better than anything they could have come up with on their own. And in the cross-silo setting, this flavor, usually the clients are always available. Like the AWS server, assuming it has electricity, assuming it has some internet connection, which it usually has, it's going to be available. It's not going to go out randomly. It's going to be available throughout training, and you can have consistent and reliable access to the server, as well as the data on the server. So what remains the bottleneck in cross-silo federated learning is communication. Because as I already said, these things are geographically separated. Maybe they're on different countries. Even if they are not on different countries, maybe the data sizes are so large that even with a reasonable internet connection, you cannot really transmit all the data. So there's some bottleneck, which usually comes from communication. How many times you communicate ends up accounting for 50%, 70% of the total cost of training models in such environments. Another feature is that clients are usually addressable and stateful in cross-silo federated learning, which basically means a very simple thing. When you say I'm taking the data from client one, you know who's client one. You can access client one in the future and say, okay, this data point came from client one. This came from the server situated in Chicago. This came from the server situated in San Francisco, etc. So they are addressable and stateful. So you can store their states and access them in the future. So this is the cross-silo federated learning problem. And this flavor, as I said, is very similar to the canonical distributed optimization problem. Data can sometimes also be partitioned by features in cross-silo federated learning, which means that maybe one of the servers or one of the data silos has only access to a particular feature of a user. Another server has another access. In the hospital example, you can think of it as, okay, there's maybe a medical lab which has access to blood sample data or the swab data of the patient, but there's a hospital which has access to historical health data for that particular patient. So now here, not only are the data points distributed across different silos, but perhaps even the features are distributed across silos. And this is something appropriately usually called vertical federated learning. I wanted to mention this because you might have heard this term going around, and this is what it is. Okay, that was the first flavor, which was similar to distributed optimization. There's also a second flavor of federated optimization. Okay, I'm largely gonna skip through this, but essentially what we are looking at here is instead of 2 to 100 or a few dozens of clients, you have millions of clients, you have millions of devices. Think of mobile devices. And again, communication and communication bandwidth and frequency are bottleneck. But more importantly, only a fraction of clients are available at each time step slow. Some of them might be in different geographical zones. So if these are like mobile phones, some mobile phones might be available only when there's a daytime in that geographical zone, etc. So moreover, these clients are not addressable or stateful. The clients might drop out without any notice, and they might not become available ever again in the training process. So whatever you want to do with the client, you do it now and then forget about it. Okay, so this is cross-device federated learning, but we don't have much time to cover this. We'd mostly be talking about the literature on cross-silo federated learning, which is going to look similar to distributed optimization, but still we are going to impose the important consideration of communication. How much you communicate, that's going to be the bottleneck. And towards the end of the talk, I'll tell you what are some additional considerations which come up when you have cross-device federated learning, like how do the results change, etc. But before doing that, let's introduce the major constraint of federated learning, which is the communication constraint. And there are many ways to capture the communication constraint, but we are going to talk about mathematical rates, and it's going to be much simpler if I talk about it in the context of a fixed model, in the context of a fixed communication graph. So this is what we call the intermittent communication model. So we have M machines, as we mentioned, and these machines do not contact each other, do not communicate with each other for k iterations. So this happens for k iterations. They can do anything during these k iterations. They can just twiddle their thumbs and not do anything, or they can make updates on their local device as much as they want to, or they can just sit and like make less updates, not k updates, maybe less than k updates. So there are k iterations when they do not communicate. And after the k iterations, they communicate, and whatever they've done between those k iterations, like during those k iterations, they communicate it to other machines so that they can also benefit from whatever computation or inference they've done. And finally, this entire process is repeated r times. So in total, there are k times r time steps, and Aadirupa used capital T in the previous talk to denote the horizon or the length of the entire process. And capital T is going to be synonymous with k times r in our setting. So this is just the intermittent communication model. So this is a specific computational communication graph. We could have thought about other communication models. For instance, like the number k could have been varying across time. But we consider fixed model because a fixed model is easy to understand. And as you'd see, there are still open questions even for like fixed k and fixed r and all of that. So this is the simplest model which is meaningful and interesting to study. Okay, so this is the simplest model which is meaningful and interesting to study, and we're gonna jump right into it now. Okay, so the easiest way to unify the two models which we previously saw, the cross-silo and cross-device federated learning, is by casting them as a distributed optimization problem. So for cross-silo, it's pretty simple. You just think of the stochastic optimization problem on each machine and then average it, and then that's your objective. For cross-device federated learning, now what you can do is, if you want to cast it as a simple problem, you can think of a meta distribution on machines. Here I call the meta distribution P, and you're actually trying to optimize in expectation over sampling machines from this meta distribution P. And okay, after you sample the machine, you also sample a point from that machine's distribution. So this is the unification of both these models, which has appeared in literature. We'll mostly talk about this objective, as I mentioned. Okay, so we've talked about the problem. We've talked about how federated learning differs from usual distributed optimization, and that usual difference comes from these additional systems and practical constraints, most of which rely around communication and also privacy. Privacy is an angle which I did not mention in federated learning because we are not going to talk about theoretically private methods in the talk, but that is also one of the initial motivations as to why federated learning as a discipline became popular, because people did not want to transmit raw data to the server, which might or might not have been sensitive. So federated learning became a solution towards that end. But we're not going to talk much about privacy. So for us, federated learning throughout the talk is just going to be communication restraint distributed optimization. And cross-silo federated learning is the thing we're going to look at. Okay, let's look at some baseline algorithms which can fit in the intermittent communication setting. And these baseline algorithms are interesting. They can be analyzed. Some of them have known analysis already. Some of them require more analysis, etc. But they are baseline algorithms because they highlight the extremes of trade-offs in distributed optimization. So the first extreme baseline algorithm is like single machine SGD. It's a very simple algorithm. You basically just run SGD on a single machine for k times r steps, and then use this model for all machines. This requires zero communication because the single machine you're working with does not even need to know that other machines exist. But we only expect this to work when the heterogeneity is very, very low. In particular, when the distributions across the clients are very similar looking. Furthermore, maybe you have some constraints on how many times you can sample from each machine. So you might not be able here in the intermittent communication, for instance, you can only get k times r samples. So maybe if you're trying to minimize the variance of your stochastic gradient estimator, this is not the best thing to do. But still, this is one easy extreme baseline, single machine SGD. Okay. Another baseline is mini batch SGD. So this is maybe more familiar to you in the distributed setting. So you run SGD with a batch size of k times m for r iterations. And this batch size k times m is not arbitrary. It is to accommodate the intermittent communication model I talked about. In particular, to see it a bit more graphically, you start with m machines and you start with some model x0. This is the initialization model. And you basically for k time steps compute the stochastic gradient at this same point x naught on all the machines for these k time steps. That's what leads to the m times k batch size. Once you get this variance reduced stochastic gradient estimator, you basically make an update in that direction. So at each communication round, you make a single update. You get a model x1, and then you repeat the process with x1. You compute the gradient at x1 and then make a single update. And then you repeat this process r times. This is a very simple algorithm. It's just, as I said before, it's SGD with a mini batch size of k times m. And this is perhaps the most common implementation of parallel SGD. Whenever you think of SGD running on some GPU you're parallelizing, this is what you probably do. The interesting thing about this algorithm is that mini batch SGD is not impacted by heterogeneity or how different the client distributions are, because you are directly getting stochastic gradients of the average objective. Like you're not differentiating between the machines, you're just getting the gradient at the same point and averaging it. So it almost acts as if you're getting the stochastic gradient for the average objective, not for a single machine per se. Okay, so that's the good thing about mini batch SGD, and it's not impacted by any heterogeneity. You can get some rate, and the rate might not benefit from making these local updates. So these k local updates, you might not benefit in an optimal sense from making those updates, but you'd still not be affected by how much heterogeneity there is in your data. Another limitation is that you only make R updates. Because of the definition of the intermittent communication model, you're restricted to make only R updates. Okay. Let's come to the third baseline algorithm. So we've talked about single machine SGD and mini batch SGD. And the third one, which is perhaps the most popular one in federated learning, is local SGD. So you run k local steps of SGD on each machine between communication. And there are total R rounds because we still have to accommodate the intermittent communication model. So you start with an initial point x0 on each machine. Then you get to some point x1m on machine m. And you keep doing this for k iterations. So you get this sequence of models which do not have anything to do with each other except for the fact that they were initialized at the same point. And at the communication round, you somehow aggregate those points to come up with the next initialization point xk. The most common way to aggregate them is to uniformly average all these points. And that tends to work well, but you can do more sophisticated things like apply some variance reduction while aggregating them or do some non-uniform aggregation, etc. Once you get this model xk, you repeat this process again for k time steps and make k more local updates and then average and keep doing this again and again for our communication routes. So if you notice this algorithm, the run of this algorithm, you might already have, this might already have come to your mind that what really stops these iterations, like these local trajectories of optimization, from diverging from each other. Like you start at the same point, but it can very well happen that machine 1 leads you in one direction, machine 2's data leads you in another direction, machine 3's data leads you in completely different direction. So the essence is that heterogeneity does affect local SGD, unlike mini batch SGD. And we expect the clients to drift between the communication routes. That's why communication becomes essential for local SGD, because communication is the means to bring together the clients which have already drifted between the communication routes in the process of making local updates. So this client drift, or whatever the effect of heterogeneity, as I like to call it, will be mild if the distributions are similar. And most local SGD analysis, like if you look at them, actually mimic SGD analysis, like simple SGD analysis. But now they operate on the average iterates. So to define an SGD analysis, you have to define a stochastic sequence of points. And now instead of looking at the machine-specific points, most local SGD analysis look at the average iterates. Now these average iterates are physically only computed when you have a communication round, but you can still do an analysis on them because this quantity is theoretically always defined, right? And or most of these analyses actually require bounding the following consensus error, which measures the gap between how much a model moves on machine M with respect to the average. Ideally, if you were making communication at each time step, then this quantity would just be 0, because you'd make an update, average, and then make an update by calculating the gradient at the averaged point. So, right, so this quantity would be 0 if you communicate at every time step, but we do not communicate at every time step, as I said. So when k is greater than 1, this would be something non-zero. And most SGD analysis try to bound this thing or this consensus error in order to give some meaningful guarantee for local SGD. We will assume, as I'm going to give some rates in the next slide, we're going to assume that all methods, single machine, mini batch, and local SGD on each machine have access to stochastic gradients with variance sigma square. Okay. So this was the theoretical setup. We've talked about the baseline algorithms, and now we're ready to talk a bit about some function classes and what sort of guarantees you can get with these algorithms on those classes. So we'll start with a very simple toy example. And as easy as this example might seem, it wasn't until 2020 that we actually characterized what sort of the min-max complexity for this kind of problem. So we're looking at a homogeneous setting. So all the distributions across the machines are the same. And we assume that our objective is quadratic. So FMs are H-smooth quadratic functions. Now, local SGD outputs a point x hat in this setting. So this is an upper bound result. You can find it in our paper, which satisfies this upper bound, HB square over KR plus sigma B over square root MKR. So you can see that there's a benefit of collaboration which appears through the second term. So if the second term is the dominating term in the upper bound, then you would linearly, in fact, benefit from increasing the number of machines. Another interesting thing is that this convergence rate is not impacted by not communicating, which is surprising because we expected local SGD to basically diverge between the communication rounds. But here it seems like all that matters is the product k times r. You do not care if k is 1, you do not care if k is infinity, as long as kr is fixed, right? So this is a surprising result. And we can not just show this result, but we can even show that when you accelerate local SGD, it's the min-max optimal algorithm to use in this setting. And the reason this happens is because quadratic setting is almost too simple. It's because the quadratic setting allows you to have linear gradients, and thus even without averaging, your iterates behave in expectation as if they were being averaged.
So a question, so what is sigma here? Did you explain that? Sigma in the bound?
Yeah, so sigma is basically the variance of the stochastic gradients for all these methods. I think so. Yeah. I think so. So in the previous talk, I think Aadirupa mentioned that you often have to control the variance of the stochastic gradient in a gradient descent-like algorithm, and that's this variance sigma squared. So in the previous talk, you saw sometimes this variance was g d square or dg squared times some constant. Here, I'm not assuming anything of that sort. I'm assuming it's something fixed sigma. One simple example is if you're getting stochastic gradients where you get the exact gradient, but add some Gaussian noise with zero mean and variance sigma squared, then the variance is just sigma squared. So that's what this variance is. You can think of sigma as measuring how much noise there is in your data, or in particular, how much different each data point is with respect to the average. That's what sigma is capturing. Okay. So this is the toy example, the quadratic setting.
One more question.
But just to follow up on that, so there is no need of any sub-Gaussian assumptions or anything.
No, nothing like that. It's just bounded variance assumption. Yeah. Okay. So this is a toy example, and this toy example shows us that in the quadratic setting, you can get optimal rate by using local SGD. But as soon as you move anything to anything beyond the quadratic setting, let's say you move to the general convex function setting, then there's a surprising dichotomy which appears, which completely sidelines local SGD algorithm. For instance, if FMs are H-smooth and convex functions, then Woodworth et al. Showed the following result, that either single machine SGD or mini batch SGD is optimal. In particular, if you run single machine SGD. Oh, by the way, one clarification, all of this is in the homogeneous setting still. So we are still talking about a setting where the distributions are the same. Okay. So they show that if you run single machine SGD, like on one machine, accelerate it, and on other m-1 machines, let's say you run mini batch SGD and accelerate it, then the optimal guarantee you can get is just the minimum of both those guarantees. And this was a very surprising result when it came in 2021, because they showed that either you do no parallelization, which is just use single machine SGD, or you just don't do any local computation. You just use mini batch SGD, keep computing, keep doing the naive parallelization strategy, and that gives you the optimal rate. Because before this result came, for 5 or 6 years, people were wondering, where does local SGD fit into the picture of homogeneous distributed optimization? This is a bit disappointing for local SGD, and it's actually a bit misleading as well, because this is a theoretical result and you can get this result for general convex functions. But often when you run local SGD in practice, you'll notice that it performs better than both these baselines, single machine and mini batch SGD. So something is clearly missing here. It's probably an assumption we need to make about a problem which we do not know of right now. But you can notice that from this guarantee, one thing which becomes clear and maybe goes back to the sigma thing we mentioned, is that the switching point between which algorithm is optimal is decided by how big sigma is with respect to smoothness or the size of the comparator B. In particular, when sigma is large or the noise in your problem is large, then you benefit from reducing the noise by collaborating across the M machines and averaging those gradients, so as to get the sigma B over square root MKR term. When sigma is low, then you benefit from making more optimization steps, because as I said before, mini batch only makes R updates, while single machine can make K times R updates. That's a simple trade-off which appears here. And as I said, local SGD cannot beat the best of both algorithms, and this presents a gap between theory and practice. And this is a simple experiment which shows that local SGD is often better than mini batch SGD. Actually, in all these experiments, local SGD is always better than mini batch SGD and single machine SGD. Single machine SGD is not plotted here, but it's always better than single machine SGD as well. So clearly something is like missing in how we are modeling the problem. And this is like a ongoing direction of work to try to understand if there are perhaps some higher order smoothness assumptions which can try to capture the effectiveness of local SGD. And why do we want to talk about higher order smoothness assumptions? Because I already showed you that for quadratic problems, local SGD is min-max optimal after acceleration. And quadratic problems have are like very smooth problems. Like in particular, if you look at second order smoothness, then they have a 0 second order smoothness constant. So one would hope that by controlling the higher order smoothness of your function, you can somehow get a better guarantee for local SGD. And both us and some other people have looked at such assumptions like self-concordance, quasi-self-concordance, third order smoothness, etc. Okay, but so this is like one major line of work which is open here. But the homogeneous setting is perhaps too simplistic. Like I started by saying that it is true that we care about using a local SGD or federated learning in settings where heterogeneity is low, but not zero, right? You'd usually not expect examples where the distributions are the same. They might be similar, but they might not be the same. So the more interesting setting is when the distributions are not the same, or the heterogeneous setting. And in this setting, we would expect local SGD to have some client drift, as I mentioned. So we would need to bound the consensus error quantity, which I showed a few slides back. Also note that, or recall that we are using like the entire thing is a proxy for a multi-objective optimization problem. So we somehow need to justify using a single consensus model. And that would also in turn help us to bound the consensus error of an algorithm like local SGD. This means that we better characterize theoretically what kind of heterogeneity our problem might satisfy, what sort of assumption it could satisfy. And there's almost been a struggle to find the correct heterogeneity assumption in the last 5 years or so. And one assumption which has been used a lot, or the flavors of this assumption have been used a lot, is a bounded gradient dissimilarity assumption. I think Aadirupa mentioned it during the beginning of her slides, which basically controls the behavior of the client's gradients everywhere. So you look at the expected objective on the client, and you look at the gradient on the client, as well as the average gradient nabla fx, and you look at the entire decision space, which in this case is unconstrained d-dimensional Euclidean space, and you want to bound these gradients. You want to bound the difference between these gradients pointwise across machines and across any model you could have chosen. So, okay, first thing which comes to mind is this is very restrictive, and it is indeed restrictive, but we started with this assumption because at that point, it was not clear if there's any setting where local SGD can be shown to have an benefit over mini batch and single machine SGD. And under this assumption, we were able to show that local SGD iterates satisfy this sort of convergence guarantee. And the first term might look very similar to what you would expect from single machine SGD if you did not have any heterogeneity. The third term is kind of like the variance term of mini batch SGD. And the second and the fourth term are the additional terms which come from trying to bound the consensus error for local SGD. In particular, from this rate, the one thing which we can conclude is that when zeta is a small, local SGD benefits from making k large or making the number of local steps large. So it almost seems like you can take k to a large number, let's say k is infinity, and the first three terms will go to 0. And now the only thing you have to pay is the number of times you communicate, right? Because this is the only term which does not depend on k. And often, as I said, in these federated learning problems, communication is the bottleneck. Sometimes I might be able to communicate only 10 times, but I might be able to do a lot of local computation on my own. So it always benefits from getting a result or trying to understand a setting where you can make k large while keeping r fixed, but still benefit from the run of that algorithm. Okay. And we showed this theoretical guarantee, and surprisingly, it's also what happens in practice. So we basically on the x-axis in this example are varying the heterogeneity of our problem. So we are making the problem more and more different on the x-axis. And on the y-axis, we are just plotting error. And what we see here is that when the heterogeneity of your problem is low, or when zeta is low, as we said here, then local SGD does have a benefit over mini batch SGD. And when zeta is large, like in the setting when it becomes very large, then you have to pay the price of client drift. You are not able to bound the consensus error very well. So then mini batch SGD takes the lead. And this is again from the paper cited here. So you can have a closer look at the experiment if you want to later. But as I said, this assumption is too restrictive. Even quadratic functions cannot support this kind of an assumption over entire Euclidean space. But this is the only helpful assumption in the convex setting we know of right now. And there's an ongoing effort to study heterogeneity assumptions. In fact, in the last 2 years alone, people have tried to address this problem. And this might be, in my opinion, the biggest problem in the theory of federated optimization. So there was this paper, in fact, titled On the Unreasonable Effectiveness of Federated Averaging with Heterogeneous Data, which we followed up by adding a still to the title because we still think this problem is very interesting and not very well understood. And yeah, so if any of you are interested, we can chat more about what are exactly the gaps and what kind of things we've tried and we know don't work, etc. Okay, so we talked about the baseline algorithms. We talked about the kind of setting in federated optimization. And we also started by talking about how federated learning, which people use without justification these days, is actually a proxy for multi-criterion optimization problems. And this is the problem you are inherently trying to solve while using federated learning. Because think about it, if a client is gonna contribute its precious data, which might or might not even be private, they should be able to get a model which is better than anything they could get on their own. Otherwise, why would they communicate? They have to pay a price to communicate. They maybe have to pay for internet. They maybe have to pay for the additional bandwidth they use, or they have to pay for additional resources they have to maintain to carry such large-scale communication. So when heterogeneity is high, we already know that this sort of a proxy is unreasonable. But can we be a bit more precise about when is heterogeneity a problem versus when it's not? And if heterogeneity is high, what should we do? Can we not benefit from collaboration or at all, or is there a way to still benefit from collaboration? And this is where personalized federated learning comes into the picture, because here trying to personalize or benefit from collaboration while acknowledging that the data can be heterogeneous. So this is the inherent objective we are looking with. And one family of algorithms which do personalization is trying to optimize the following problem, where you have a model X, as well as you have a model Y1 to Ym. And the Y model is the machine-specific model. The X model is the shared model across the machines. And you're minimizing the same objective you were before. But now you're combining the X and Y models in a manner so that you can personalize. And as I said, X is the shared model and Ym is the model on machine M. Intuitive way to think about it is X is perhaps what's shared between the machines. With the model X, you can capture what's shared between the machines. With Ym, you capture what's different between the machines. So this is a very simple characterization of personalized federated learning. But if you look at the literature which has appeared in the last 7 or 8 years in personalized federated learning, most of the algorithms can actually be recast in this optimization framework. So with this in mind, there are actually 3 regimes we can characterize here. When you have very low heterogeneity, when DMs are very similar, we expect federated learning to work well because these quantities are going to roughly be the same. These min values are going to roughly be the same. So either local SGD or mini batch SGD or even single machine SGD will be optimal. That's what intuition tells us. And the correct heterogeneity assumption, even though it's not clear so far what should be the heterogeneity assumption so that it's not too restrictive, it's a safe bet to say that there is at least some heterogeneity assumption which can capture this low heterogeneity setting. Okay, there is a moderate heterogeneity setting which often gets overlooked. In this regime, we still hope to benefit from collaboration. That is, we can benefit from talking between different machines, communication between different machines. But if we insist on using a single consensus model, that might be too naive and might in fact lead to some sort of a min value of the objective, which is much higher than the multi-criterion optimization problem. In this regime, though, even though there's still theory which has to do a bit of catching up to do here, personalized federated learning is still promising because you can still try to leverage what is common between the machines and what is distinct between the machines. And empirically, there have been dozens of papers which have shown that personalized federated learning has a much better trade-off with respect to heterogeneity compared to just using federated learning with a single consensus model. And then there's a third regime, very high heterogeneity regime, when your distributions are just too different and you do not hope to benefit from collaboration at all. And more often than not, the problems we try to solve do not lie in this setting, because when they lie in this setting, you would probably not talk about federated learning at all. So it makes more sense to individually optimize on each machine in this setting because their distributions are too different. Just don't talk to each other, just optimize on your own. And as I said, it's still unclear what heterogeneity measure I can put on an axis and try to quantify where you enter one regime versus another, right? So it's still unclear what heterogeneity measure you have to use here. To give you a very naive intuition for this, let's consider a very simple problem. Let's consider the mean estimation problem, which has been studied for decades and which we reasonably understand both statistically and computationally. So this is a problem you have on machine M. You're trying to optimize this objective. There's a squared loss. You're getting samples from DM, and then you're trying to minimize the squared norm error with respect to some sample you've taken from this DM and your model X. So this is a convex objective. In fact, this is a strongly convex smooth objective. In fact, it's a perfectly conditioned objective with condition number 1. Okay. Let mu m be the mean on machine M, and let mu be the average mean of these machines. Then I claim that the following heterogeneity notion is natural, which basically captures how far the means are on each machine with respect to the average mean. And this is one tentative assumption which can actually capture the 3 regimes when personalization makes sense, when federated learning makes sense, etc., etc. And there have been some theoretical works which have exactly looked at this measure of heterogeneity to try to characterize when we are in one regime versus another. But there are some limitations. I have cited one of those works on the slide, but this work only looks at losses like logistic losses, where I'm not even sure if this heterogeneity notion is the most natural one, but that's what this does. Intuitively, you can think, okay, when your means are very close, you would expect to benefit from collaboration because while you communicate and average your samples, you're basically killing the noise which comes from sampling from the distribution. When the means are a bit further away, you can still try to maybe first converge to the average of the means and then try to converge to the separate means from the average mean. And you would expect that converging to the average of the means is already most of your job done because most of these machines' means might be clustered around the average mean. But if you have 2 machines, their means are far, far from each other, then you cannot really benefit from collaboration, right? Can you? Because now the sample complexity of estimating the mean on the first problem has nothing to do with whatever samples you might get from the second distribution. So this is one notion of heterogeneity, which might be promising, and there are some works trying to characterize these regimes in the setting. Okay, so that was the federated learning part of the talk. I've not talked about the analysis, besides mentioning that there's something called consensus error, which people try to bound. As you might have noticed, as compared to online convex optimization, which is very well understood, we understand in most settings matching upper and lower bounds for online convex optimization. Federated learning is still much nascent, and there are many open challenges here. And one of the biggest challenges I mentioned here is characterizing the correct data heterogeneity notion, which can capture different regimes for when you should do federated learning versus when you should do personalization versus when you should not collaborate at all. So that's one of the biggest challenges. And another open challenge, which I mentioned, is trying to characterize like some higher order smoothness assumptions, which can sort of capture why local steps are beneficial or why local STD works well in practice. So these are two open challenges, at least in the convex world here. I skipped on some slides which talked about some non-convex literature. But surprisingly, like in the non-convex setting, we understand almost matching upper and lower bounds for some algorithms. And this is work from last year in Europe. And it's surprising because usually we understand the non-convex theory much after we understand the convex theory. But it seems like in the distributed setup, the convex hard instances are actually harder. Anyway, so that's like a very fast preview of the literature on federated optimization. And now I want to talk a bit about sequential decision making. So to link back to whatever we discussed in the first talk, as well as the motivation and why are we talking about online federated learning. Okay, so we started with this objective where we said that, okay, these distributions across the machines are fixed across time, they do not change. And I think Aadirupa already mentioned that this distributional assumption can be very restrictive. Like if you have a hospital setting, it does not make sense that your interventions on the population do not have any impact on the population. They usually do. There's stuff like herd immunity, whatever vaccine trials you're running are going to have some impact. And thus your study is going to be impacted by whatever actions you take on the population and in general, the passage of time. So this distributional assumption where you have some fixed stationary distribution can be a bit restrictive, which is why we would like to now reconcile online and federated optimization with each other. And one way to do this is to define the kind of laws which Aadirupa also mentioned in the first part of the talk, where you have some objectives, FTMs, which are convex and appear on machine M at time t. And XTM is the model you play on machine M at time t. And this model can be based on the history available on the machine. And you're comparing against a fixed comparator, which is shared both across time and across machines. So it is important to share this comparator across the machines, because if you do not share this across the machines, then this is a completely decoupled problem. Like there's no collaboration happening, right? So we are operating in settings where it makes sense to also do so, right? There's a theoretical model, but then there's a theoretical model for settings where sharing the comparator makes sense. Like if you have, for instance, different departments in a finance firm which are trying to predict the market, then they might all want to compete against the same strategy, which might be a fixed S&P index fund, right? So X star is shared across the machines. Again, to remind you that we are in the intermittent communication model, the way it works is you play the model XTM on machine M at time t, and you do this for k iterations. And then you are allowed to communicate. You are somehow allowed to share information, all the information you gathered during these k time steps with other machines. And you do this for our communication routes. Okay. So we start with a surprising limitation of collaboration in online federated optimization. And this is in the setting when you have exact gradient access. So you have like first order access to these objectives FTMs on machine M at time t. So for instance, let FTM be G Lipschitz. So in accordance with the notation we've been using. Then Aadirupa showed you the construction where the average regret is lower bounded by GB over square root T. And in fact, even though that construction was for a single machine, there's a way to extend that construction to the distributed problem as well. And that's what we do in our recent paper. We first extend that construction to the distributed setting, and we show that there's a lower bound which does not improve with the number of machines. This essentially means that when you have gradient information, you cannot really benefit from communicating across the machines. And this is also a lower bound which can easily be attained by running online gradient descent on each machine. To see this, note that if you run online gradient descent independently on each machine without any communication whatsoever, then you have actually completely decoupled the problems, and you are optimizing this average objective where you're competing not against the shared X star, but against the XM star of that machine, against the XM star which arises out of the sequence of that machine. And this objective is always going to be higher than our distributed average regret, where X star is shared across the machines. Because when X star is shared across the machines, perhaps it's not as good as a model, because you're not allowing X star to personalize for that machine, right? So if you can, with non-collaborative online gradient descent, minimize the above objective, then of course you can also upper bound the lower objective. And we already saw in the previous slide that you can get an upper bound of GB over square root T for the serial optimization problem when there is no distribution, no distributed aspect whatsoever. And that is going to match the lower bound of GB square root T. So this essentially means that collaboration is not beneficial when you are in the online setting. And it's a bit disappointing, and you might even feel like this contradicts the stochastic setting results, which I showed you a few slides back. But that's not the case. Actually, the problem is harder. When you're looking at the online problem, you're actually looking at an adaptive problem. You could have an adversary which could look at all your previous models and give you a harder function at any time t. So their lower bound is definitely going to be higher. And that's precisely what's happening here. The lower bound is actually much higher than it would have been if you were just looking at a stochastic problem where the distribution was fixed. Okay, so can you somehow elevate this by making more assumptions? Like maybe if you make your functions Lipschitz and smooth, then maybe you can benefit from collaboration? No, so we show that there's still no benefit of collaboration even if you make them Lipschitz and smooth. And for more details on the lower bound and how these reductions work, we have a big section in our paper which talks about these reductions and how the lower bounds are derived. Okay, so is there then no hope in the online distributed setting? Is there no hope to benefit from collaboration at all? And there is actually hope, and it comes in the zeroth order or the bandit feedback setting. So recall the bandit feedback setting, which Aadirupa just mentioned. It's the kind of algorithm which she described, both for single and multi-point feedback, was like a stochastic gradient descent algorithm, right? Because instead of getting access to the exact gradient on that machine so that you could run online gradient descent, now you sample from this ball or unit ball uniformly a vector and then create a stochastic gradient estimator for a gradient. So it's very much like online stochastic gradient descent if you think about it. And if you can distribute a stochastic gradient descent in the form of either mini batch SGD or like local SGD, you can also distribute online stochastic gradient descent. So that's precisely the algorithm we are going to consider. And we're not going to talk about the single feedback setting that's in the paper, but I'm quickly going to jump to the simpler setting of 2-point bandit feedback because it's also possible to get better rates there. And intuitively, as you saw, the finite difference in intuition is much easier to understand in the 2-point bandit feedback. So to further simplify, let's even consider just linear problems, not all Lipschitz problems, just linear problems. Linear problems are the smoothest possible problems you can think of. So these are the problems we consider. So these are the cost functions we have at each time step. So there's a adversarially perhaps chosen vector beta tm at time t on machine m. And that's what characterizes the loss ftm on machine m at time t. And the machine queries its oracle, it's like whatever bandit feedback it wants on 2 points, xtm plus delta utm, xtm minus delta utm. So same notation as previously. Then it receives the zeroth order feedback, which is the function value at these points. And it computes the stochastic gradient estimator much the same way like we did before. But now is where the difference arises. So when you are in the serial setting, you just make an update with the stochastic gradient estimator with some step size. But in a distributed setting, or specifically in the intermittent communication setting, the updates differ when you communicate versus when you do not communicate. So when you do not communicate, you still do the same thing. You just make a local update with the stochastic gradient. But when you communicate, then instead of making an update with GTM, you make an update with the average gradient GT in that communication route. And the hope is that now this frequent or intermittent communication is going to help us in the same way it helped us in the stochastic setting, that is through some variance reduction mechanism. And when you assume that you have some Lipschitz cost function, so beta TM is L2 norm bounded, you can actually get the following average regret. So now it comprises of 4 terms. The first 2 terms are sort of standard in the multi-point bandit feedback literature. So Aadirupa showed you how to get the second term when she said, okay, you have M point feedback. So think of it as you have M point feedback on your objective. This is the term you'll get. But you also get 2 terms because of not communicating. So when K is equals to 1, that is when you are communicating at each time step, then these 2 terms are actually 0, and you get a min-max optimal rate in the 2-point bandit feedback setting. But when K is greater than 1, you still get those terms. The hope is not lost yet though, because when dimension is large enough, you still are in a setting where the second term dominates all the 3 terms. And when the second term dominates, you can see a linear speed up in the number of machines, which is precisely the kind of speed up we are after. So what we've shown is that there is indeed a benefit of collaboration in the 0th order or bandit setting for distributed linear problem. And we, as I said, we also analyze the single bandit feedback setting. It's there in the paper. We also generalize our analysis to Lipschitz functions and or smooth functions, but there are still many more open questions here. Like this area is very nascent, as Aadirupa mentioned, and our paper is perhaps one of the first ones trying to like formalize what sort of lower bounds and upper bounds you can hope to get. And to maybe try to give you a picture of how nascent this area is, P2 is like this is basically a directed graph which is trying to capture min-max complexities of different problems. And the lower a problem is, the easier the lower the min-max complexity of that problem is. So it's an easier problem. And P2 is the problem which I mentioned in this talk, which is the online federated optimization problem. And P9 and P10 are the stochastic versions of federated learning problems, which I mentioned in the first part of the talk. So you can already see that these stochastic versions of the problems are much simpler than the online version of the problem. And there are actually many problems in between these problems, which might be relevant for the particular application you have. And none of these have been studied. So there's actually a lot of work left to be done in this area. And if you think about it, most federated learning applications are actually online problems. There are very few problems where you have a fixed collection of data set which does not change over time, but the distribution does not change over time, it's static. So most interesting problems like self-driving cars, or maybe even something as simple as keyboard text prediction on a mobile phone, or improving on a voice assistant agent, are online distributed problems. So there's a whole environment of problems which needs to be understood here if we want to deploy meaningful algorithms in these applications. So I have about 2 more minutes, so I'm going to quickly talk about some other directions. So we did not talk much about cross-device federated learning when the machines actually are sampled from some meta distribution P. And one additional complexity which arises in this setting is that the sampling of machines is another source of variance for your problem. So your gradient estimator is one source of variance, but the sampling of machines is another source of variance which you have to really control. Or you could think of it as a source of like heterogeneity. When the machines are very different from each other, then sampling fewer machines is gonna be you're gonna have to pay for it as compared to sampling many more machines, right? Another direction which I briefly mentioned is vertical federated learning, when the features are also distributed. So you somehow need to make sure that however you are collaborating, however you are aggregating the models on different machines, they are cognizant of the fact that the features are also distributed. And finally, there can be more explicit models of distribution shift and robustness. Some of them have started appearing in the serial convex optimization literature, like distributionally robust optimization, etc. But there's still a lot of work to be done in the distributed setting, like the non-serial setting, like how to have maybe a slightly easier notions of distribution shifts, because we already saw that in the completely online problem where the functions are allowed to be adversarial and arbitrary at each time step, there is no benefit of collaboration in the first order setting. So perhaps that problem is too hard. Perhaps with more assumptions, you can indeed benefit from collaboration. Finally, it's a very important problem, but hasn't received much attention, is how to incentivize clients to participate in the federation. Because often you have clients which have good data, some clients have moderate, mediocre data, some clients do not have any data of value at all. So a part or a coalition of the clients might feel like they are doing most of the work while training these federated learning models. So how to incentivize to sort of ensure that everyone wants to participate? One way to do that is to monetary incentives. There are other ways people have been trying to do it through privacy incentives. One another way is through differentiating the kind of models you give to these devices. And we have a recent work which would be on archive soon, which also tries to look at data incentivization. And finally, combining all these considerations with sequential decision making is the real challenge here, because federated learning, while stated in the usual stochastic setup, is not a stochastic problem. Most of these problems are online problems. So with this, I can conclude. We gave a very brief introduction of online and federated optimization, as well as the problem at the intersection of those two problems. We understand online convex optimization considerably well, which is why we can give very tight upper bounds and lower bounds for that setting. But there are still many open questions in federated optimization, and this remains an active area of research. I hope that you could understand two broad open questions here. One, it is understanding the correct heterogeneity measure, which can capture when we transition across different regimes. And another problem is coming up with higher order smoothness or higher order regularity assumptions, which can sort of highlight the benefit of making local updates. And yeah, so there are theory practice gaps in the homogeneous setting as well as in the heterogeneous setting. And finally, most federated learning literature, and if you've been aware, there are actually thousands of papers coming each year these days. It only considers like non-sequential problems. So there's a lot of work to be done here, and we hope that you will be interested in doing some of that work. So that's all.